Okay, so this is our third topic, and just because I'm recording the video, this is my the Mod 30 class. So I'm recording the Mod 30 class version of graphing today for anybody who watches this another time. So one of the things that we need to use a lot in physics is the concept of a graph. And before I get to that, I want to do just like a basic idea of other places you might see a graph. For example, let's say that you worked in the world of finance, and it was your job to make money. And so you decided to try to figure out which stock to buy. And you found a graph. And there's a stock that's looking like this. Does this look like a good stock to buy? Well, maybe. I mean, it would have been really good to buy it right here, right? If you could have gotten on the ground floor, that would have been fantastic. But does this look like a company who is on the rise, who's being ultimately successful? I'd say, yeah, I'm seeing a lot of growth in this company. Now, I can't guarantee, by the way, that like they won't all of a sudden have a big crash, right? Because really, what is this graph probably, like I didn't put axis labels on it, by the way, right? But what is this graph probably referring to? What would you probably put on this axis over here? Probably how much money the stock is worth. And on this axis, yeah, probably time, right? So, I mean, unless the stock craters, it looks like this is a graph that's trending in a positive direction. However, if I had to choose to buy a stock and I found a company that did this, maybe it's not a good, maybe it's a good time to buy because it's really low right now. But in general, would you agree that this stock has been tanking over time? Maybe it's not a good idea. Now, I mean, either way, you're kind of gambling, right? That's the idea of the stock market. But graphs are a great way of visually representing what's occurring. Now, yesterday when you guys watched my YouTube video, I gave you questions like this with word problems. And that's one of the challenges of physics, is sometimes just giving you examples in words, that's really limited, right? But if you can have some sort of pictorial format that gives you an idea of what's going on, I'm going to skip ahead in my slide to say this one right here. Sometimes that gives more information for those who are visually inclined. You know what I'm saying? Like if you're the person who likes to see a picture and it helps, let's talk about these two graphs right here. Look at this graph here. What is going on in graph 1 over here? It says it's a position versus time graph. So let's talk right here at the very beginning. What's happening right there? That's where the person is, I don't know, starting from, right? And then as time goes on, this person's position is going further away, further away, further away, further away, further away. It looks like whoever this is walking away. Does that make sense? And I can like interpret that by kind of reading the graph and saying that they're getting, does it even give a direction here? Yeah, it says they're going to the right, I think. So this person here just kept moving to the right. Here's another graph. But this is now a velocity versus time graph. Right here when the graph starts. Was the van stopped? Or already in motion? Yeah, this would be like, this is already in motion because look, where is the velocity? It's right there at 20. So it's like we're like cutting right to the middle of the car chase, and this car is already moving 20 meters per second. And what's happening in this first little section here? Yeah, it's accelerating because it was going 20, now 25, now 30. Right? Now I could tell you that in words, but again, words are kind of limiting, right? But if I can give it to you in a graphical format, hopefully we can understand that in this section right here, we had accelerated motion because things were getting faster. And sorry, that's kind of, I've got a lot of ink on there, so let me erase some of it again here. So section 1 here started at 20, then 25, then 30. We're getting faster. What's happening in section 2? Yeah, we're going constant motion, uniform motion. We're going the same speed. Now the car is just on cruise control, right? For the next amount of time, they're just always going 30 meters per second. What happens in section 3? Decelerating, yeah, because we're going from 30 down to 25. What happened right at this point right here, right at the 45-second mark? It came to a stop, perfect. Do you guys understand what I'm beginning with here, though, is that graphs, I think, are inherently better sometimes than giving you words, right? There's a time and place for both, right? But a graph gives you kind of a visual interpretation of what's happening. I mean, really, I think the best thing would be to go outside and watch whatever's occurring, right? If I could actually have a videotape of this airplane moving, or a videotape of this car that's moving, that would help, right? But in lieu of that, a graph gives you a lot of information. That's my goal today. We're going to talk about how to read and interpret graphs and what we can do with them. So I'm going to hop back to the slides I skipped here. Here's the first thing I need you guys to know. If you are ever in my class, or really any science class, working with a graph, there is a few conventions that really almost always apply. The first is that you need to have a title. Like every graph should have some sort of title on it telling you what's happening. Pretty common thing to put on a graph. The next thing that most graphs, not most graphs, all graphs really need is a label. Right? And by label, I mean like on the sides of your axes, you got to tell me like what's happening. You know how when I first started, I gave you like a stockbroker graph of like money and time, right? You should really label that and say that on this axis you have height apparently, and on this axis you have time. But you should like label what the heck we're talking about. You know, otherwise, the graph has no meaning to us. You also, in physics, should really include the units. So like if your height is right here, it should be like your height in meters. I feel like there's too much glare on the board. Is that fair to say? Should I try this? Can you see that better now? Okay. I feel like I can't even see it that well. So yeah, over here, yeah, that's height. Oh, that was height in inches, isn't it? And this is time in weeks. But do you guys get what I'm saying here? We need to have some sort of labels. The last thing we need to have for sure is a scale. And by scale, I mean you should have some numbers along the edges like 0, 2, 4, 6, 8, 10, 1, 2, 3. Like if you don't put some numbers along the side, it really doesn't mean much. The last thing you could include is a key. But you really only include a key if you have more than one thing in the graph. You see how there's like 4 different lines going on here? Because there's 4 different lines, they recorded 4 different people here. I mean, unless you have multiple different items here, you might only have one line. That's fine. You might not need a key. But I would say in general, make sure you have a title, labels with units, and a scale. Those are the basics a graph should have. Sound good? Actually, I haven't taught them over here yet. I'm going to try this. Okay. The next thing I need to make sure you guys are familiar with is the idea of independent versus dependent variables. You've probably heard the word independent and dependent in everyday life. For example, like I have little children. They are called, literally, like my children are known as my dependents. Why do we call them dependents? That's a good word. I want to use that word. They rely. Right? Anything that relies on something else is the dependent variable, right? If I don't give my kids food, they don't know how to cook yet. My 1-year-old, if I don't like change her clothes, she can't change her own clothes, right? As a weird example, counter to that, you guys are probably now fairly independent because your parents probably don't change your clothes for you anymore. Oh, that'd be really awkward. Anyways, right? Like maybe they still make your food for you, but do you get what I'm saying here between dependent and independent? So here's how that applies to a graph. We always put the independent variable on the x-axis and the dependent variable on the y-axis because the y thing, whatever it is, always relies on x. Use this graph as an example. This is a graph about a car wash, and it talks about how much revenue gets made based on the number of cars. Even just listen to how I said that. The revenue is based on the number of cars. Does the number of cars depend on how much money you make? Well, no, it kind of works the other way around. If you have more cars, you will make more money. It doesn't really work in the way where if you have more money, more cars will show up. That's not how this works, right? Can I say that one more time? In one of the scenarios, I'm saying if more cars show up, then you will make more money. That's the way that this would work, right? It doesn't work in the way that if you have more money, more cars will show up. I mean, maybe that'll happen, but that's not really the reason why. You get what I'm saying? So you always have to identify who depends on who. Long story short, in physics, it's almost always time that goes on the independent axis. Because what does time depend on? Nothing. Time always goes on just regardless, right? But the amount of force, for example, let's say I used force on this axis. The amount of force that occurs really depends on how long I push for, right? For example, let's say that I have this chair right here. Let's say that I push for 1 second, or let's say I push for 5 seconds. Didn't the amount of time make a difference? Right? So time in that silly little example there is what caused force to occur, just like cars caused revenue. So you just always have to make sure you know that terminology. Sound good? Cool. Okay. No one's really shaking their heads at me. So we already talked about these graphs. The first part of my lesson today is really going to be all about making sure that you can like look at a graph and just basically in words describe what's happening. So like we already did, here the car is speeding up. Here the car is going the same speed. Here the car is slowing down, and right there at the very end, the car stopped. One of the challenges I find when teaching kids about graphing, though, is that it's not like there's a formula I can give you. It's really a lot of common sense. It's a lot of reasoning where you just look at it and go, well, that's the answer, because. You get what I'm saying there? No. So I want to do a lot of examples today. Let's try another couple here. Let's say that I give you a scenario. Let's say that a person is standing over here or sitting over here by a fireplace camping. And I asked you for a velocity versus time graph. You can hardly even see it, but if you can't tell, there's a little orange line right down there at the bottom. Why does it make sense that this graph is just a straight line right along the bottom if a guy is just sitting here while camping? Oh, I love that, because time is still going on, but he's not moving, right? So his velocity is nothing. But what about right here? Now you're paddling in a canoe, right? Well, let's say you're one stroke, right? One on both sides, right? Well, when you're doing that, you're going to be going the same speed the whole time, but now you're actually moving. See how this was a nice flat line because you're going the same speed? Uniform motion, yeah. This is uniform motion. But this one right here would be non-uniform motion, because hopefully you can kind of piece together how this works. Here, they're starting at rest. So you can see right here, they weren't moving at all, and now they're moving faster and faster and faster and faster as these runners are getting up to speed. Yeah. Technically, yes, because uniform motion occurs whenever you don't have an acceleration, and since this one right here had no acceleration, also no velocity, but yeah, in theory you could call this one uniform motion. Great question, thank you. So, did that make sense? Like I said a slide ago, a lot of this is common sense. I hate to use that word because it kind of implies that if you don't get it, that you're dumb. I'm not saying that, so please don't think that, but hopefully you kind of already get the idea intuitively. So here's an example. Here's what I want to do. I want to give you a minute. I want you to look over this example right here and see whether you could, like in your head, identify what's happening. Right? Here's a graph. Identify whether things are going forwards or backwards or speeding up or stopped. And then let's like write a story to this. And I'll give you a minute to think about it first. Does that work? So just look at the graph and figure out what you think is even happening. This is a different graph, eh? One of the reasons why is that the previous graphs I gave you, I call them L graphs. But this isn't an L graph, it's like a T graph. Why do we not just use the top quadrant? Why the bottom quadrant? What's happening at first? Represent the negative sign. Which way are we actually traveling? Backwards, south. South more specifically. Look at this. It told you right here this was the velocity. Can you see how there's, I know it's maybe a little blurry here, but see how it said meters per second north? That means that any time that you're in the positive section, you're traveling north. So just for the sake of argument, why don't I make north be, which way's north? Like roughly that way? West side. Where's the bridge here? That way is more or less west. So why don't I say that this is north more or less over here? So, okay. So I'm walking north, but hang on, no, we're not actually walking north at first. We're really walking south. So we're also picking this up in action, right? Because as we begin, whoever this is already walking south, right? We're beginning in motion. And what's happening in section A? Are they going the same speed? Or are they getting faster? No, they're going faster because they were going 2 meters per second, and now they're going 4. So if I were to like visually represent this, not only are they moving, but they're speeding up. And then what happens now when the line flattens out at B? Are they still in motion? Yep, they're still in motion, but now they're going the same speed again for a little while. They're going to continue to speed up even more now, right? So like get a little bit faster, go the same speed. Get a little bit faster in section C, and then they're going to go the same speed again. So if I were to ask you where the uniform motion sections are, that would be B and D. B and D are where we have uniform motion because they're going the same speed. But during A and C, they're speeding up, but they're speeding up in the south direction. This is probably the hardest part of the graph to talk about here now. What's going on in this section here? Not yet. Close. In this section right here, they are still traveling south. So remember my demonstration here where we were speeding up, keep going the same speed, speeding up, keep going the same speed. Well, we haven't turned around yet. Where is the single location where they did turn around? Right here. This is the spot where they turned around. Right? Because here is the difference between going south and going north. What happened during this section right here is that they slowed down. Right? Because they were traveling 6 meters per second, then 5, then 4, then 3, then 2, then 1. Can you kind of visualize that? So if I were to like me demonstrate this again, here we go. I need lots of room here. Section A, I'm speeding up. Section B, same speed. Section C, speeding up. And then I'm going to start slowing down. Does that make sense? This section right here was slowing down. But was I still traveling forward? Yes. And at this very moment, I turned around and I started running the other direction. Because this section right here for E, am I going the same speed or accelerating? Accelerating. I turned around and I accelerated the other direction. And then section F, then I go like a flat constant speed again. Could you follow that? It's kind of cool, hey? That's one of the advantages of graphs, is that you need to be able to interpret what's going on. Right? So we'll practice. And if I need to, I will run around the classroom, I guess. Okay, let's try another example here. Let's say I gave you a graph that looked like this. Remember, look at the labels. This is a position time graph for a dragster. Well, position refers to like where your location is. Look, here you went like that far in 1 second. But now you've gone a little further, and a little further, and a little further, and a little further. Are we going the same speed? This is acceleration. Can you kind of visualize that? You went this far in 1 second, a little further, a little further. Now you're getting much further. Now you're getting much further. This would be a good example of acceleration. So sometimes you can have graphs that are kind of curvy-like, and they are accelerated graphs. Okay. I need to sit down because I need to look at the board for the next example here. So what we're going to do today is discuss a concept that ideally you guys learned back in Math 10C. Okay. Everyone here has hopefully taken Math 10C, I hope. Okay. If not, can we chat at some point? Because I need to fill you in on the blanks on some math concepts. The equation is y equals mx plus b. Hopefully you're somewhat familiar with this from a math class. The idea is that say you have lines that are nice straight lines. We can actually calculate something known as slope. And slope is often the m variable, if you recall this from math class at some point. The idea of slope. Slope is how steep the graph is. For example, look at these two graphs right here. Which of these two graphs has more slope to it? Well, hopefully you're in agreement it's graph B, because it's got a little more steepness to it. Okay? And what we've actually discovered, and I'll show you why in a bit here, but let's say that you have a position time graph. If you know how to calculate the slope, a position time graph slope is its velocity. This graph right here was traveling like a nice leisurely velocity here. But this blue graph right here, it's actually traveling much quicker. If I were to have a graph that was like this, was very, very steep, that graph is the graph of someone who's traveling really, really, really quickly because they're traveling a large distance in a short amount of time. Does anybody remember the formula that you might have learned back in grade 10 for slope? That's the one I was looking for, but whatever you said is probably going to work too. The most common ones are either y2 minus y1 over x2 minus x1. Is that probably what you were going for? Yeah. Or the more common one we use is the phrase rise over run. And hopefully Hopefully you're familiar with this. Again, I don't have time to like reteach you all a grade 10, but if you have a hole in your knowledge, can we talk? Because we got to fix that, right? So, but if you get the idea of rise over run, I want to talk a bit about formulas for a bit. What was the formula for velocity? Just like the most basic one we learned. Okay, distance over time. But hang on a sec here. The distance right here, that's basically position. And your time right here, that is time. If we were to find the rise amount and find the run amount and make kind of a triangle out of it, like you probably did in a math class at some point. Well, the rise is your distance. The run is your time. Isn't d over t, isn't that going to be a velocity? So, long story short, if you remember how to do slope from grade 10, we can actually calculate some values by looking at a graph. And that's what I want to do over the next few slides. I also have a note here down below. Let's say I give you a velocity time graph. So say I give you a graph of velocity and time. What's the formula for acceleration? Well, velocity over time. So if you make this become your rise value and this become your run value, you can actually calculate your acceleration the same way. So let me try an example here. Oh, no, I'm going to do the example on this page, I think. I'm going to erase some of this, just to make sure you guys remember how to do this. By the way, does anybody have questions so far that you might be wanting to ask? Yeah, I can write that out again. I'm not going to utilize that. I like rise over run, but it was this, y2 minus y1 over x2 minus x1. I like rise over run. I think most kids have heard of that one before. So here, let's do a little challenge, I guess. Yeah, basically it's d over t is what we're looking for. Let's take the yellow graph right here, or the orange graph right here, and let's calculate how fast this object is traveling. So I'm going to make a triangle out of the yellow graph. And I won't use yellow, I think, because you can't see it, I'm betting. Let's use red. How much rise does this triangle here have? Well, looking at the graph, it looks like the height of this is about maybe 100. If you guys would agree on that. And then the run would be how far across this triangle goes, which to me looks like 20. So 100 divided by 20? 5 meters per second. There. I now know how fast the first object was moving. It's actually pretty easy. You just need to do two numbers divided by each other. But I can do the exact same thing for the blue triangle. Let me just do a second time here. See how there was this blue triangle in here, right? What's different? Well, let's just write it again. We got rise over run. How much height did this triangle gain this time now? It was more than 100, right? 110? Can I go with 120 just to make it a nice round number? But yeah, whatever you interpret that as. I think it's up to about 120. But did it take as long to get up to 120? Well, no, it was 5 to 20. How far is it from 5 to 20? 15, yeah. And I did this one earlier today, so I don't need my calculator. But for those of you who do have a calculator, 120 divided by 15, I believe, was 8 meters per second. But doesn't that make sense? That the first object was kind of a nice leisurely pace. The second object didn't even start for 5 seconds and then got even further, even faster. So that's calculating a slope. And so that's a skill I need you guys to work on, is being able to look at a graph and tell me just how fast an object is going. Now, this causes some problems, however. And one of the reasons why it causes problems is that not all graphs are linear. Many graphs are considered to be non-linear. You guys know the word linear? If I'd ask you to put linear into people words, you'd say linear means it is straight is probably the most common word that comes up. Yeah. So if it's a nice straight line graph, it's a linear graph. So say we have a curved graph, just like this one that we talked about back here, where it was kind of like a little rounded. We have a problem. Because if we want to try to calculate the velocity, we really can't, because the velocity was always changing anyways. This graph right here had acceleration. So we're going to use what's called a tangent. And so I'm going to spend a few minutes discussing first what a tangent is, because maybe you don't know. A tangent is whenever you have some sort of curved line, usually a circle, and what ends up happening is normally you're wanting to travel around the circle like this. You guys ever heard the phrase, you go off on a tangent? Ever heard that phrase before? Like, say you're having a conversation, and all of a sudden someone starts talking about something altogether different, And like the phrase we use is, wow, that was really, you went off on a tangent there. What a tangent means is that we draw a line mathematically like this, that's like going just like completely the opposite direction, where it was supposed to go around a circle like this, and we've taken this point right here, and we've made it diverge on like a straight line. And what makes the tangent unique is that it just barely grazes the curved section here. And you're making a second line that just barely touches. See how that works? This line right here is known as a tangent. And I think that's where the phrase came from, is because it was supposed to go this way, and the tangent means that you're going a different way here. So here's why that matters. Right here, see how there's this curved line right here? I don't possess the ability to make a triangle out of the curved line. But what I can do is I can draw just a little triangle based on a tangent, and the tangent just barely grazes the edges right here, and then I can calculate a slope. But we use different terminology. We call the slope right there the instantaneous velocity. And the reason why we have to use that phrase, instantaneous, is because it's going to be different here than here and here and here. Because remember how we said this thing was getting faster and faster and faster? The velocities will be constantly changing. If you were to look at the slope of this line right here, and then the slope of this line right here, hopefully you'd agree that the second line is a little bit steeper than the first one because you're going faster. So I've got an example slide on the next one I want to walk you through that kind of explains how you would then calculate a slope based on a curvy line, not a straight line. Okay. So first let's talk about what's even happening in this graph right here. This is an ATV approaching a river. What's happening right here at the beginning? Is he already in motion or starting at rest? Looks like he's starting at rest because we're starting at 0, right? And then in 1 second, he traveled 15. And now he's traveled 25. And now 30, and now 35, and now maybe 36. What's happening at the end here? He's slowing down. You got a nice good start going here, and then slowly but surely it's kind of leveling off. Right here, if I were to draw like another line, can you imagine how this would be like a flat line straight across? That flat line is straight across because it's a position time graph, means that it's not even moving anymore. All right? He started 0 meters away, got up to about 36 meters away, and isn't really moving anymore. So do you guys understand? Can you see how this is actually deceleration? He's slowing down. What I want to do in this example here is I want to try to calculate the velocities first. So here's how I do that. I'm going to use a tool on my board here, a line drawing tool. And I'm going to draw a line that looks something like that. Can you guys see how at this location right here, that location right there, I've drawn what's known as the tangent line, where basically it just barely cuts right through it, like it just touches and grazes the edge. That's known as the instantaneous acceleration. And I'm just going to make a triangle out of this real quick. So I'm going to make a triangle that goes from probably about here to there. Can you see how I made a little triangle out of that now? Quick calculation. Rise over run. So approximately. Again, this is going to be approximately, but like I would say the run that I've accounted for is about 2 along the bottom. And the rise is from 5 to 25. 20, okay. And 20 divided by 2 is 10. So I would say at this particular moment, my velocity is 10 meters per second. Let me do it again, because I'm going to do this 4 times. Hopefully by doing it 4 times, you'll kind of be able to see how this looks. Come on, pick all this up and move this somewhere else here. I'm going to take the same line right here. I'm going to try to draw a dot at this location right here, and I'm going to try to use the exact same sloped line right there. Is that a really good tangent now, though? Can you see how like it kind of like slices to the middle of the graph? That's not very good, hey? I need to adjust the slope of this line a little bit. So to do that, I'm just going to modify this maybe to there. There, that's a better sloped graph now. Wouldn't you guys agree? Now it kind of fits the tangent, but now it's going to be a little bit less steep. It's kind of declined a little bit. So I'm going to do the exact same thing. I'm going to try to calculate a triangle. And so I think I'm going to draw a triangle like this. I'm going to draw over to here and maybe up to there. And I'm going to draw my triangle here now. And I'm just going to erase and change my rise over run values. So it used to be 20 over 2. Let's get rid of all this stuff we don't really need. What's my new rise and my new run? So it looks like my run is actually still 2, hey? How much height did this triangle get now, though? It went from 10 to 25, give or take. So call it 10 to 25. What's that, 15? What's 15 divided by 2? 7.5. Did my velocity stay the same? No. I used to be going 10 meters per second. Now at this location, I think I'm going 7.5 meters per second. Let's try another one. I'm going to do this 4 times. So I'm just going to erase this stuff right here. I just made a nice looking triangle. You can make your triangle, so long as you make a triangle. I made one that like kind of fit nicely. Does that make sense? Here, let me try to explain that as I do the next one. If I pick up this and try to put it in the location there, I should draw the dot here. I'm trying to put this location right there. You guys can hopefully see here that my, this is not a really good tangent again, right? So I'm just going to modify the line a little bit, make it a little less steep, pick it up and maybe put it there. Now you asked why did I make the run 2? I could have made the run anything I wanted. So I'm just going to try to make the best triangle I can here. So here, let me make a different triangle. Let's make this go all the way over to there and up to there. So I've made like a nice triangle out of this now. So now this time the run is 3 because I'm going from here to there. And actually, I think the rise is still 15 though, isn't it? Because look, it went from 15 up to 30. Right? So this time I just randomly, do you get the answer to my question there? Like I'm arbitrarily choosing how to make my triangle. As long as it's consistent, it won't matter. 15 divided by 3 means that my slope at this point right here is now 5.0 meters per second. Anyone want to hedge a guess as to what the slope right here would be? Can you pick up on the pattern? We started at 10. We went to 7.5. We went to 5. What do you think the next one's going to be? 2.5 is the right answer. And anyone want to hedge a guess as to what it would be probably here? Yeah, and 0 I can actually make sense of. Look, if I were to try to draw a tangent line right here, it would be completely horizontal. Because again, what was happening to the ATV in this example? It was coming to rest. It was stopping, right? So the question actually asked me to calculate the acceleration. What was the acceleration of this object? Close, really close. The raw number was 2.5, but it's negative 2.5. Why the negative? Because if you actually gave me 2.5, it would have been accelerating. So this was going down by 2.5, and the unit we use is meters per second squared. So that skill that I just showed you there 3-4 times there is called drawing a tangent line and calculating what's known as the instantaneous acceleration. Why does it have to be an instantaneous acceleration? Well, because the acceleration, an instantaneous velocity. Wrong word, sorry. We're calculating instantaneous velocity because the velocity is always changing. It was different at every single point. The only time you ever have a consistent velocity is if you have a graph like this one here, for example, or this one here, where it's a nice straight line. Right? But if you get one of these curvy line graphs, like this one right here, the velocity is always changing. And so therefore the tangent right here is different than the tangent right here. So you kind of have to do it like one step at a time. Now, here's what I said to the class first thing in the morning here. This is new, and one of the downsides to me delivering the lesson to all of you at once is that maybe I'm going a little too fast still, and like I'm looking at the clock here going, okay, Chris, you got to finish this in 10 minutes, right? So if that didn't make sense, I need you guys to let me know later, and I'll try to explain it better, right? You can also rewatch the video, or like tomorrow we're going to do an assignment on this. You'll get some practice at it. Okay? But like hopefully my first time through made sense. I once heard an analogy that compared teaching to bowling. You know how in bowling your goal is to knock down pins? So the goal here is basically I'm going to try to knock down as many pins. In this analogy, knocking down pins means like helping all of you understand. But like I understand that like if there's a few kids here and there where like if you didn't fully get it, well, just like in bowling, you just got to take another shot at it, right? So please understand if you don't get it after 10 minutes of explanation, It's okay. Just tell me that I need to do it again. Okay. Last topic here. Oh no, we're not to the last topic. I have another example here, but we're actually just going to discuss this one. This one's a lot easier because if I want to try to calculate acceleration in this graph right here, remember how the previous graph had like a curved line to it? Well, this one's not a curved line anymore. This one's straight lines. I should be able to calculate just by drawing a little triangle right here, the slope in section 1. All I got to do is rise over run. It looks to me like the rise is 10 and the run is 5, so I think that there's a positive 2 slope right here. Isn't it a lot easier when the graphs aren't curved? Right? All you got to do is just like 2 quick, looking at graph numbers, divide them. What's the slope in section 2 though? Yeah. Now, it's 0 meters per second squared because we're looking for acceleration, which means this van is still traveling, it's just not speeding up, that's all. And then in this last section, let's do the exact same thing. Let's make a little triangle out of this thing here. It looks like the rise is about 30. It looks like the run is about 15. You guys able to catch where I got all that from? 30 over 15 means it's 2. But wait, 2's not right. Okay, negative 2. Why is the negative so important? Because it's slowing down. It's decelerating, right? So hopefully you guys will agree. Calculating slope actually when it's a straight line graph isn't actually that hard. But if I give you one of these curvy line graphs like this one here, it's a little more challenging, but we can do it still. This one right here, it was from 30 to 45, which is 15. By the way, maybe today's is as good an example as any. Do you guys see why it might be useful to maybe have notes printed off? It depends on the lesson as to whether you want the notes, because again, I'm kind of going at a speed that kind of covers everybody. But yeah, it's just something to think about. If you want to have notes in advance, they're online. We have photocopiers downstairs, right? If you want them, they're there for you. Okay, here's my last example, then we're going to take off for the day. It's also possible to calculate something known as the area under a graph, area under a curve. And this is a very specific, very unique example. We only use it on velocity time graphs because what it tells you is the displacement. Let me explain the theory first, then we'll do the question. The theory is that we know that velocity is equal to distance times time, right? We know this formula. And if you ever do a rise over a run, we can then calculate velocity as a slope. But let's say we get rid of that concept here. Let's say that we want to solve for displacement. Well, mathematically to solve for displacement, you would then bring time up to the other side over here, and you'd make a formula where your displacement is velocity times time. Well, anytime that you're multiplying things, this really fits the same formula of area equals length times width, where because you're multiplying things, if you were to make a geometric shape out of this thing, see how I'm kind of making like a big square type thing out of this? If I were to calculate my length and times it by my width, what happens when you take a length times by a width? Well, you get area, right? But what is my length on this axis? My length is actually a velocity. What is my width on this axis? It's actually a time. Well, we know velocity times time is a distance. So this is the last activity we're going to do, and I hope I don't come across as like making this be like if you don't get this, you're dumb. I'm not saying that, but this is not one of the harder tasks we have. All you have to know how to do is calculate the area of shapes. That's it. If you can like do length times width and stuff like that, this is actually pretty easy. So let me try an example for you, because sometimes kids freak out at first going, whoa. Our goal is to take the same graph and try to calculate the distance traveled. Now, look, this was a velocity time graph. If we were to calculate slope, what's the slope of a velocity time graph? Acceleration. Yeah, and it would be rise over run, but sorry, I didn't phrase that very well. If you take velocity and divide it by time, it's acceleration. So if you were to do rise over run on this graph here, it would give you acceleration, which is not a bad thing to know, but it doesn't tell you displacement. What we have to do is calculate the area right here. And if we do that, it will tell us how far we've traveled. The only problem is I have like kind of a weird shape here. So here's how you solve this. Yeah, you make some triangles and squares out of it. I'm going to use colors. I'm going to make a little triangle right there. I'm going to make that little purple triangle. Well, what is the formula for area of a triangle? 1/2 base height. So I'm just going to do a little bit of mental math here. In purple, so this is just a little triangle over there in the corner. It's 1/2 of the base, which I think is 5 across. Can you see how that's 5 across there? And the height looks like it's 10. So 1/2 of 5 by 10. 5 by 10 is 20. I'm getting ahead of myself. 5 by 10 is 50. Cut it in half, it's 25. That means nothing, by the way, right now. We just got to like keep going. Okay, so I'll come back to this a little bit later, but this 25 on its own really doesn't mean anything yet. I've only accounted for just a little shape over here. Why don't I do another shape? Why don't I do a triangular section over here? See how there's kind of a triangle sitting over there? Well, again, that triangle, I'll draw it over here, is 1/2 of the base. Okay, 30 to 45, 15, and all the way up there is 30. I don't want my calculator on this one, I think. I don't have that memorized. 15 times 30, cut in half gives me an area of 225. Still doesn't mean anything yet, by the way. So I'll have to just kind of keep plowing through. I can now make, like, say, a big square-like shape right in the middle. I'll use green now. Say I were to drop this down and make a big square right through the middle. What's the formula for a square? I don't know, just length times width, I guess. So for the big square right in the middle, length times width would be, okay, it goes from 5 to 30, so that's 25. And the height of this thing was 30. So the big square, 25 by 30, is 750. Still not useful yet. Got one last section. Let's use blue. The last section I haven't accounted for is a little thin little rectangle over here. You can see that. And that thin rectangle has the same formula, length times width. So I believe the length is 5. The width is 5, the height is 20. I don't need a calculator. 5 by 20 is 100. Here's how this problem is solved then. Remember how the whole point of this is that velocity is distance over time? But if you take distance as equal to velocity times time, that's what we really have here. Velocity multiplied by time using appropriate area formulas. See how I always was multiplying numbers by each other? Sometimes I cut them in half because like they were going downhill or uphill. But if I just add up 25, 225, 750, and 100, that will tell you how far this object has moved. So last step, and then I'm done for the day. 25 plus 225 plus 750 plus 100 gives me a grand total of 1100. And that's going to be in meters. This now tells you how far the object has traveled. So that's what's really useful about this graph now, is I know information about its velocity, its time. If I wanted to know about acceleration, I would calculate slopes. And if I want to know how far it traveled, I do areas of shapes. Okay. Now, here's where I find a lot of students get a little frustrated and confused. If you can understand why we use areas of shapes, that is fantastic if you get why. But if it doesn't even fully make sense as to why we're doing that, but you just know how to do it, we'll take that for now. Does that make sense? So if you don't fully get why we're doing all this shape nonsense and you're like, I don't get that, I'll explain it again later. But I would suggest that like calculating areas of triangles and rectangles, like my daughter's in grade 1. She's able to do most of that, right? So if you don't get the rationale though, can we talk later and I'll try to explain it better? Okay, that's our lesson. I'm going to pause the video here and then give you some final words and then we'll go.